Hi everyone, welcome to this presentation on the exploration of Mars by rovers. My name is Mohamed Nassif, a graduate student at Georgia Tech with the Department of Aerospace Engineering, pursuing a PhD of the Space Systems Design Lab. This presentation will consist of an overview of the different mission types, a brief history of Mars exploration, and detailed description and results obtained from the Mars rover missions. There are four basic types of planetary spacecraft missions: flybys, orbiters, landers, and rovers. Flybys are spacecrafts that are in orbit around the Sun and are so launched to encounter our planetary body in its trajectory. They usually send for initial reconnaissance to understand a prior unknown body. This is before we invest more significant amount of resources to try to get the flyby to spacecraft to get into an orbit around the planet. We want to know more about the planet, whether it's a rocky planet or a gaseous planet, or does it have kind of atmosphere or no atmosphere. Orbiters are spacecraft that enter into an orbit around another planetary body. They're designed to operate for a long time, some in excess of 10 to 20 years. They usually conduct extensive studies about the body and send back this data back to Earth in order to plan for surface missions. Landers are spacecraft that reach a particular location on the surface and communicate with Earth. They collect data about the surface, interior, soil, and atmosphere if there's any. Rovers are mobile versions of landers. They're remotely controlled by Earth, and they collect measurements on the surface, rocks, and atmosphere as well. They're able to cover larger distances than with landers. So here's a brief history of the Mars exploration missions prior to 2000. The first exploration of Mars started with the Mariner program, when Mariner 4 in 1964 was the first spacecraft to conduct a flyby of the planet. Further flyby missions were conducted by Mariner 6 and 7. In 1972, Mariner 9 was the first spacecraft to enter into an orbit around another planet. Viking 1 and 2 were two missions that each consisted of an orbiter and lander. Both successfully launched and landed on the surface in 1976, providing extensive data on the surface, as well as the atmosphere and the weather. The orbiters, as well as conducting science experiments, also acted as a relay for each of those landers. The Mars Global Surveyor mission was launched in 1996. It was dedicated to map the entire surface of Mars. It has been in a Martian orbit since 1996 and has been successfully mapping the surface since March of 1998. Pathfinder was a lander mission along with a small rover, Sojourner, that landed on the surface in 1997. It had great scientific success and public interest, while also providing the basis for which many subsequent surface missions were planned. Now let's get to Mars exploration post-2000. In 2001, a spacecraft named Mars Odyssey entered Mars orbit. It was later renamed for 2001 Mars Odyssey in honor of the movie 2001: A Space Odyssey. It serves as a communication relay from which the future rovers and surface missions used to communicate back to Earth. It is still in operation and is the longest serving spacecraft at Mars, and it is expected to last until 2025. Spirit and Opportunity are twin rovers, part of the Mars Exploration Rover mission, arriving on Mars in 2004. They are two of the most successful Mars missions, returning valuable data about the planet, as well as functioning well beyond their planned lifespan. Mars Reconnaissance Orbiter is a spacecraft designed to study the geology and climate of Mars, as well act as a relay for surface missions. In 2013, it provided over 200 terabits of science data, which is more than the entire data returned via the Deep Space Network, a tracking station at JPL, during the previous 10 years. Due to its ability of high data transfer rate, NASA aims to use it for as long as possible. The Phoenix Mars lander was launched in 2007 and landed in Mars in 2008. It is the first in the series of NASA's Mars Scout program. Phoenix was designed to study the history of water and habitability potential in the Martian's Arctic-rich ice-rich soil. The solar-powered lander completed its 3-month mission and kept working until sunlight waned 2 months later. The mission officially ended in May 2010. The Mars Science Laboratory was launched in 2011. It had a rover named Curiosity It was designed to assess whether Mars ever had an environment able to support small life forms called microbes. MAVEN, which stands for Mars Atmospheric and Volatile Evolution, was the second mission in the Mars Scout program. It launched in 2013 and entered orbit in 2014. MAVEN's mission is to obtain critical measurements of the Martian atmosphere to further the understanding of the dramatic climate change that has occurred over the course of Mars' history, as scientists believe that the planet once had a habitable environment a long, long time ago. InSight, interior exploration using seismic investigations, geodesy, and heat transport. NASA does love its acronyms. Is a robotic lander designed to study the deep interior of Mars to see why the red planet evolved differently from Earth, as it is one of the solar system's rocky planets. This is the most recent mission that was launched in 2018 and landed in 2019 and has landed in 2018 and has been currently drilling and taking measurements. Before we describe the Mars rovers, let's understand what goes into designing them. What are some of the challenges that one needs to consider? For starters, it's the science payload. What kind of science instruments do you want? Pretty much all planetary missions require some sort of scientific basis. So what is the value of the reason you're going to invest in a rover, in an orbiter, in a lander? So it's important to remember, it's important to get together a reason as to what science do you want to collect, whether it's drilling, it's sample collection. Are you going to use cameras to take a lot of pictures and different kind of filters? Are you going to collect samples and break them down and analyze its composition? That's important to first understand because that determines how you're going to collect the samples, where do you want to go, and things like that. Landing location influence. It's very important to understand what environment you're going to land in. If you're going to go towards the polar locations where there's an ice-rich environment, you're going to design the rover slightly different. Most rovers have been landed pretty much around the equatorial region, so you know it's going to be a rocky terrain, sandy, rocky terrain. Power and electronic systems. Are you going to invest in solar energy? Or are you going to use RTGs, which stands for radioisotope thermonuclear generators, which is basically generating power through the decay of a radioactive material, which is more complex than solar energy, but is also expected to give more power, and you don't have some of the considerations that you need with solar energy, such as what if my solar panels are covered? How do I get energy? What if it's cloudy? What if there's a dust storm? Communications with the Earth. You can communicate directly from the surface of a planet to Earth. Remember, it's going to be slow data rate, and it's going to take a long time for all that data to be transferred. Are you going to have a relay, such as transfer that data between the surface and an orbiter, which is a very short distance, and then use the orbiter to relay that data back to the Earth? But you also remember that there's a time delay. It's about 5 to 20 minutes difference between when a command is sent on Earth and is received on Mars, or when it's sent from Mars to receiving on Earth. And that depends on how the planets are aligned in different times of the year. You need to also consider mechanical system. Number of wheels, what kind of wheels? What is the material that you're going to build the wheels with? What are the gears that are used for this? The suspension system, the actuators. If you have any mechanical arms, how are you going to retract? What's the flexibility? How rigid are you going to make it? And then you have the thermal management systems. Mars, just like any other location on Earth as well, it goes drastic weather changes. It goes from being really hot to being really cold. So you want to keep the systems warm during the winter and cool during the summer, so that all the scientific instruments, all your communication systems, your mechanical systems, they're still operating as intended. So first up, we have the Sojourner rover, which landed on Mars in 1997. It is a small rover that traveled with the Mars Pathfinder mission. It was originally only designed for 7 sols. Sol is a Martian day, which is slightly about 40 minutes greater than an Earth's day, but it lasted 83 sols and traveled about 100 meters from the landing site. It had no direct communication to Earth, so the only way to communicate with Earth or receive commands from Earth was to talk to the base station, which was the lander, and then have the lander talk to a relay, orbiter relay, or directly to Earth. It is the first rover to be used on another planet, laying foundation for rovers that followed. It's purely powered by solar energy. It analyzed rock compositions. The mission ended when the base station lost Earth communication, which also ended the Pathfinder mission, but the rover was still working during its last communication. So it is presumed that the rover also died due to not having any communications. As shown here, this was a simple rover with minimal instruments, power, and communication systems. The antenna here is what allows it to communicate to the lander. It worked on a walkie-talkie system where you would have the lander talk to the base station, but the base station couldn't talk until the lander was finished communicating its results, and the lander would have to wait to send its commands. It had about 6 wheels and 2 scientific instruments, few cameras for navigation, and taking pictures. This is a Martian sunrise that was captured by Sojourner. This is a photograph that's taken by Sojourner of a Martian rock. Scientists at that time believed that the texture on this rock suggests that it was slowly shaped over time by wind. This is a graphic of the Sojourner rover driving around the Martian surface, and as it rolls up one of its wheels on a rock. This was taken by the base station Pathfinder. Next up, we have the Mars exploration rovers. It consisted of 2 identical rovers, Spirit and Opportunity, launched in 2003, landed in 2004 on 2 separate launch vehicles. They carried identical instruments that were designed to explore the opposite side of Mars. They originally were supposed to last only 90 sols and about half a mile of driving, but both exceeded that number. For Spirit, it lasted about 5 Earth years and about 5 miles, with the mission ending in 2010 after getting stuck in soft sand and unable to get out. For Opportunity, it lasted 15 Earth years and drove approximately 28 miles from its landing location. It entered hibernation in 2008 due to a dust storm and was not able to reboot. Both were powered by solar energy, which gets affected by intense Martian dust storms, which is one of the reasons why Opportunity, because it relied on solar energy and those dust storms would cover the location, it would not be able to get enough solar energy in order to generate power to last. So that is why it entered hibernation and it never recovered. Spirit found evidence of minerals associated with water environments, while Opportunity holds a record for most distance traversed than any planetary body away from Earth. Clearly, this is a more advanced rover than Sojourner, especially in its capabilities as well as power and communication systems. It did not require a lander for communications. Spirit and Opportunity could communicate to an orbiter or communicate directly with Earth. It had multiple camera systems for navigation as well as imaging of surfaces and samples. It's powered by solar panels, so they are right on top without any obstruction from other components. It had a small arm that allowed it to go closer to rock samples, as shown here. So some of the images and results from Spirit. This is a 360-degree image of the terrain that was surrounding Spirit in 2004. It was assembled from images that were taken from the navigation camera. This image was taken of the Bonneville crater after Spirit finished a drive. This is an image of the soil at the bottom of the shallow depression dubbed Laguna Hollow, where the Mars exploration rover Spirit would begin trenching. Scientists were intrigued by the clustering of these small pebbles and the crack-like fine lines, which indicate a coherent surface that expands and contracts. A number of processes can cause these materials to expand and contract, including cycles of heating and cooling, freezing and thawing, and rising and falling of salty liquids within a substance. This allows scientists to understand what were the different processes that could have happened on Mars. This is an image of a rock that was nicknamed the Adirondack, and an image of the rover arm moving towards before it went to go collect more information about it. This is a map of Spirit's distance traveled. This was its landing site, and it traveled 5 miles all the way here where its mission ended. Next, we have Opportunity. This is a meteorite that was captured by Opportunity and was the first meteorite to be ever identified on another planet. The spectrometer on Opportunity revealed that this basketball-sized meteorite was composed of iron and nickel. This is the photo of the Erebus Crater that was captured by the PanCam of Opportunity. On the western ledge of the Erebus Crater, this ledge was called Payson, which has a diverse range of primary and secondary sedimentary layers. This looks very similar to some of the rock formations that you might find on Earth. Of course, Opportunity was one of the first rovers to take a selfie. This image was nicknamed blueberries. These rock formations were nicknamed blueberries by NASA. They're really small. The entire image is only about 1.2 inches across, but these rock formations provided evidence that Mars was once wet. This is navigation camera's raw image. The NASA's Opportunity rover looked back at its own tracks in 2010, approximately 6 Earth years or 3 Martian years later. This is a traverse map of Opportunity. It landed in the Eagle Crater and drove all the way to the edge of the Endeavour Crater in Perseverance Valley, where it began to hibernate and never rebooted, and that remains its resting place. Next up, we have Curiosity. Curiosity launched in 2012 and has been currently operating on the planet. It's much bigger than Spirit and Opportunity. It's a size comparable to a Mini Cooper. It has 17 cameras, an advanced scientific payload, and a robotic arm that is used for sampling and drilling. It's the first rover to operate on nuclear power, not solar power. So it uses RTGs to generate power. This allows it the ability to support enhanced scientific experiments that were not possible in Spirit and Opportunity due to limited power, and it can also travel much faster. It can travel about 660 feet per sol, or about 200 meters. It has also a longer planned lifespan. It is equipped to search for clues to life. It has spectrometers for surface composition characterization, environmental sensors for current condition on Mars, as well as cameras for surface and terrain imaging. Curiosity also utilized the first use of a novel entry, descent, and landing system that acts autonomously for precision-guided entry and soft landing, and this is what will also be used on Mars 2020 rover. Here is an image of Curiosity with its main components labeled. There are 17 cameras on the rover with 7 cameras on the mast, this thing right here, 9 on the rover, and 1 on the arm. These cameras are configured for different purposes. For example, on the mast, there are 4 navigation cameras, as labeled as nav cams. There are 2 cameras in the front on the rover for hazard detection, and then you have the camera on the arm for close-up images of rocks and samples as the arm drills. Notice the pattern on its wheel. When these wheels roll on the surface, they imprint in Morse code the letters J, P, and L. The NASA facility Jet Propulsion Laboratory in Pasadena, California, that was responsible for the design and construction of Curiosity and the operation of Curiosity. This was designed so that, apart from, you can have JPL being spelled out all across Mars in Morse code, they can figure out the distance traveled if any visual landmarks were unavailable. This was a selfie taken on Mars by Curiosity in January 2018 using its Mars hand lens imager. These are 2 sides of wind sculpted ripples of a Martian sand dune. This looks really similar to some of the deserts that you might see in Africa or in the US. This is a photo of a sunset that was recorded by Curiosity in 2015 from the Gale Crater. Curiosity pauses at the site from which it reached down to drill into a rock called Buckskin on lower Mount Sharp. This is an image of Curiosity's wheels when it first landed on Mars. As you can see, they look healthy. They look all in one piece. This is 4 years apart. In 2016, NASA used the Mars hand lens imager to check the condition of the wheels once again to see if there's any deterioration. Clearly, you can see that there are holes over here that were not that's not here, and this Scientists and researchers believe that this was due to, in 2013, Curiosity encountered really sharp rocks and terrain that was really hard to maneuver around. So they had to go through it. That was one of the main reasons that there are multiple holes in this area, in these treads. The current team members are actually keeping a close eye on these, frequently taking images of these treads to figure out if they're breaking apart sooner or later. Tests that were conducted on identical wheels showed that when these treads, these zigzag treads, when 3 of them are broken, it means that the rover has used up about 60, the wheels have gone about 60% of its useful mileage. So you only could extend up to about 40% of the time that all been used up. Here we have identical models of the 3 types of rovers that have already exploded on Mars. Sojourner, right here, Spirit and Opportunity, and Curiosity, around a medium-sized rock, and an adult male for size comparisons. As you can see, that each rover built up upon the foundation that was developed in the rovers and missions previously. For example, technology demonstrations from Sojourner allowed Spirit and Opportunity to be launched and landed and operated, and lessons learned from this mission allowed Curiosity as well. Now we're going to take all of those 3 and have our next in the upcoming rover, March 2020, also called Perseverance. It is slated to launch this summer, no earlier than July 20th, in about less than 30 days from Cape Canaveral aboard a ULA rocket Atlas V. It is very similar to Curiosity, but it's a more robust rover with upgraded and additional features that is launching in summer 2020. It utilizes Curiosity's engineering team to keep the major components the same. Some of its new features include a novel sample collection and caching system. So samples will be collected, stored, and dropped off at strategic locations for a future sample return mission. It is equipped to investigate surface geological processes, search for signs of habitable conditions, and biosignatures of past life. It carries similar instruments to Curiosity with upgraded technology. Key objective is to make measurements and technology demonstrations for future human expedition. Perseverance is also carrying a technology demonstration of a Mars helicopter called Ingenuity for powered, and it will be the first demonstration of any kind of powered flight on another planetary body. As shown here, Perseverance is very similar in size to Curiosity, but it is heavier to do additional instruments as well as a stronger wheel design to prevent abrasion that we saw earlier. It has more cameras as well, with 23 on this rover. The arm has also been reinforced to hold heavier science tool and as well as a powerful drill. These are the science instruments on the rover, some of which are the cameras. This is where the sample caching system is located. The arm extends and takes the drill core sample and brings it back to the rover, where there's a smaller internal robotic arm that moves the sample to a sealing station where it is hermetically sealed, so nothing can enter or leave. The tubes are stored in the belly of the rover until the location is determined to drop it off, that is surrounded by landmarks, so easy to determine when a future sample return mission is launched and can return it. It's easy to determine where these samples were dropped. Here we have the power system for Mars 2020. They also utilize RTGs. You can see these fluid loops right here that is utilized to take the heat away from the RTGs and distribute it around the system to keep them warm, or take it away and distribute it to the environment when you need to cool down the rover. Here are the communication systems for Perseverance. It has 3 antennas, a ultra-high frequency, a high-gain, and low-gain antennas. The ultra-high frequency antenna right here is used to communicate with the rovers. The high-gain antenna is steerable, so it can point in any one direction, so it can point directly towards Earth. And then the low-gain antenna, it's omnidirectional, so it can take radio signals from any side. It is primarily used to receive commands. This is March 2020 during construction and assembly at JPL in California. This is Ingenuity that is stored in its configuration sitting atop the rover. This is an image of the inner workings of March 2020. It's the variant in the belly of the spacecraft. As you can see, it's a very complex and sophisticated system. This is Mars 2020 before it's being enclosed in its aeroshell that will protect it from the Martian atmosphere during re-entry. The assembly was done just a few days ago in Kennedy Space Center, Florida. These are the landing sites of successful NASA missions, both landers and rovers. As you can see, Opportunity and Spirit were landed on opposite sides of Mars. Perseverance and Curiosity are somewhat close. We have the Viking 1 and Viking 2 that were also on opposite sides of the planet. Phoenix, which was, as mentioned, designed to study the Arctic ice-rich soil, was closer to the polar ice caps. And Perseverance will be landing right here when it launches in a month and gets there about February 2021. I'd like to acknowledge all the images and the information have been taken from Jet Propulsion Lab JPL, NASA, Planetary Society, Space.com, and Spaceflight.com. These have been excellent resources. You can go and search them online and actually see some interactive graphics for these rovers and investigate more about technical details if you're interested. On behalf of the Georgia Outreach Team for Space with the Georgia Spacecraft, thank you for listening to this talk.